Hello, um, welcome to another video on energy power picture of wave. You may remember that energy in a one wavelength distance of a wave on a string um, for a harmonic wave we found to be this expression. Okay. Um, Now you can actually get the rate at which energy is being transported from this expression by using what is called steady state. So suppose we focus our attention to this part of the world, just that space. Well, this as wave comes in, you can see that this wave, there will be a next moment will look like that, and the next moment will look like that. So it will go through the full cycle. However, at any time it's still one wavelength, right? Still one wavelength. So the energy content of this does not change over one period. What's happening is energy is coming in, some energy is coming in, so this much energy must be coming in, and that same amount of energy must be leaving the system. So you can think of it that way. So in a steady state, in a situation where energy is overall not changing, energy may be a function of time, but it's over one over this one distance, in this space, the energy remains the same. So the rate at which energy is coming must equal to rate. So if I equate that, so what period do I need? Okay, so this much energy is at that much time. So the power that's, the rate at which energy is flowing, some average, this is not instantaneous, some average is if I took E lambda and divide by the period of that. When I do this, I'm going to get 1 over 4 pi, and omega will go lambda mu omega cube a square. You can write this in quite a number of different ways, and we can see it written some other ways just in a minute. So this is for instance, if I did this as a say if I write this 2 pi over k, so I can write this 2 pi makes it half here, and 1 k and 1 omega over k is equal to v for a harmonic wave, right? Which is v of p, phase velocity, and which is also is equal to square root of t over mu, and so we can actually write this as square root of t times mu omega square a square, and t times mu is called characteristic impedance. Called impedance, our characteristic impedance of the medium. So it's the same thing. I can write another way. All right. So the power can be written, because there are so many relationships with omega and k. You can replace one by another, and still it look different, but it's the same values. All right. So this is an overall picture of what energy and power is happening in the wave. However, we can do a little bit more detail, like force, work, picture. So if we want to do that, we have to look at a model in which the wave is generated somewhere. So let's see the wave is being generated at, so we have at x equal to 0. So we have this string which is very long and tied somewhere there, and this end is tied to the tip of a vibrator. We'll call it wave generator to be general. So wave generator. So as it vibrates, it generates a wave down the line. Parenthetically, if you had a very infinite string and you had a wave generator going up and down, it will send a wave this way, another wave this way. So we will do that example sometime in the future. But if I just have one side, and then this will just generate that way. That's the situation. So you're looking at it at x equal to 0, and I'm looking at just the particle that's attached there, how much work is being done, what's the force on it. So if you look at that particle, that there's a force on the particle by the vibrator, I suppose pulling it down, and there's a tension force. So if you look at this tension is acting on the generator, right? So if generator is a system, the string is trying to pull it that way. Of course, this must balance that force, so it's pulling that way, and we're looking at the force on this, which causes the acceleration in this direction. Acceleration in that direction is the y component of that. So if I look at y component of this force that's on the string, so this is equal to minus ty, which is minus t sine theta, which is minus t, approximately tangent theta. And then if you look at tangent theta, you look at the particle itself, particles of the string itself. From there you have a delta psi this way and delta x that way. So this just becomes minus t d psi dx, but we are working at x equal to 0. Okay. But the ty is the force on the generator. So force on the generator, this is the force on the string, and so the force on the generator is ty. So this is the force that the generator is applying on the string. So how much work it is doing? So work by generator. Well, the force is applying times the displacement, right? So Fy on a string times delta y of the string. It's in the same directions, and this is the same thing we're calling d psi. So it is going to do, we can call it dw for a small displacement, and it's going to be minus t d psi dx at x equal to 0, and this will be d psi, but this is happening at x equal to 0. This is the displacement of the particle at x equal to 0. Well, the rate at which this work is being done, rate of work, is the instantaneous power. So this much happening in some small time, and this psi is a function of x and t. So I will convert, or if I divide by dt, I convert that into a partial derivative, d psi dx x equal to 0, and this is supposed to be at x equal to 0. So if I divide d psi with dt, I'm going to be at x equal to 0. So this is the instantaneous power, and we want to find out if psi is a harmonic wave. This, if you look at it, so far I didn't assume any shape of the wave, right? I didn't say psi was cosine omega t or something like that. We didn't do anything, right? So this is completely general up to here, and I want to look at what this looks like for harmonic wave. So for harmonic wave, psi will be, so for harmonic wave, psi will be some amplitude A cosine kx minus omega t. Right? So it's I can do x derivative and t derivative and find out what it looks like. So I need psi x derivative and want to evaluate x equal to 0 at any time. And so this will be, take an x derivative, this goes to minus sine and k comes out, so minus a k, and then when you take a sine minus omega t, it becomes plus. So this becomes a sine omega t. And then the psi dot of 0t, like this one. So if we take a dot, I get a cosine to sine, and then this this minus comes out, and then when x equal to 0, another minus comes out. So that's a minus a omega sine omega t. Take a product of those two things, so I get pt, instantaneous power, I get a minus with a plus. So the work done by the generator is a positive work. So t, I get a square k times omega sine square omega t. So this power actually is not the same at different times. It is a harmonic function. It's a harmonically varying function. So we want to figure out what the average power is, P average. So here is this varying over, for the period omega over 2, because it's square function, right? So I can just average over one period. So if you look at what comes out, average is over one period is half. That one you need to show. Do you know how to show that? Well, here's what you have to do. When you time average over some time, and says you're averaging over a period, so it will be a period, and you integrate over t ft dt. So try doing that, and you'll show that that's equal to half actually. So that's equal to, this is half t a square k omega. That's average power. That doesn't look like these formulas, but we talked about just now that actually this is nothing but those formulas. Let me show you how it's the same thing. I want to go to square root of t mu, so let's break this up at half square root of t square root of t, and then have a square and k. K, I don't want to have a k, so omega over k is the speed, which is square root t over mu. So k is omega square root of mu over t. So square root of mu over t times omega, and this omega makes a square. So this t cancels that guy out. So I get half square root of t times mu omega square a square, and which is same as the z we have defined over here, characteristic impedance. This is exactly the same, z omega square a square. Pretty cool. There are so many different ways to write the same thing. So this is the average power that this generator must be inputting into for the wave to be continuing in time, right? The wave doesn't kind of one pulse. It's not a pulse situation, but it's a continuously wave is this vibrator is going up and down, and then continuously is producing the wave in time. Well, in the future, we will when you do a little bit more work, we will be able to do, okay, what happens if I just give a pulse, this wave generator just pulses and then stops. What happens in the string? Well, a pulse will be generated, and it won't be like this, but the pulse will just go from place to place. This is pretty cool. It turns out the string is non-dispersive. This particular string model is non-dispersive, and we will learn more about dispersion. In a non-dispersive medium, the shape of this pulse will just continue. So if it was pulse over here, then you move over here, but that's not realistic, right? In more realistic situation will be you give a pulse and it must spread out, and that's called dispersion effect. We will talk dispersion. It's a very important topic at some time in the future. Okay, so